Hi there. My name is Irina, and I'll be presenting our work, Adaptive Testing of Computer Vision Models. This is joint work with the wonderful Gabriel, Scott, and Marco. Even state-of-the-art computer vision models can still have unexpected failure modes, which I'll call bugs. For example, Google's popular Cloud Vision API can fail to generalize to new environments. While it can detect stop signs, it sometimes fails at detecting stop signs covered in snow. Models can also exploit spurious correlations that we're not aware of. Massive vision transformers, we find, still spuriously correlate kitchen countertops with microwaves. One thing we'd like to do is to have a fast process to test for and identify these bugs. This enables us to intervene on the model before deployment. For example, developers can collect additional data from difficult topics for fine-tuning. And in general, knowing about failure modes is critical for deciding where models are safe to deploy. But how do we test for bugs? Unfortunately, this is challenging. Existing evaluation sets are typically small, and so they underestimate out-of-distribution vulnerabilities. Prior work has explored automatic testing, such as using synthetic perturbations. For these methods, we pre-specify a suite of augmentations to test models with, such as brightness changes or adding different weather effects, and then we check whether model behavior is consistent after these augmentations. While fast and cheap, these methods introduce image artifacts, and they can only test behavior along those pre-specified axes we have perturbations for. An alternative approach is to use human-in-the-loop testing, such as red teaming. Users can manually scour the web for images to test the model with and then report undesirable behavior. While this is flexible and finds vulnerabilities otherwise missed, it's slow, expensive, and limited by user creativity. It's often challenging for users to simply imagine where models might fail. In this work, we present adaptive testing for computer vision, or AdaVision. The goal of AdaVision is to address some of those shortcomings of human-in-the-loop testing. Rather than having users generate tests and topics to explore on their own, we offload some of this work to foundation models, asking CLIP and GPT-3 to propose what topics and images to test with. Users then steer the testing process by deciding which of these proposals to actually use and by scoring model behavior. I'll now walk through how the process works in more detail. Suppose a user wants to test an object detection model on stop signs. First, we use CLIP to retrieve relevant images from a large unlabeled dataset, such as Lion 5 billion. Next, we run the model being tested over the retrieved images, and we present the user with the model predictions. The user then labels some number of these predictions or tests for correctness. Here's where adaptive testing begins to differ from unassisted human-in-the-loop settings. After we've identified some model failures, we adapt the retrieval process to look for similar images within the topic. We do this via embedding arithmetic. The process then repeats. CLIP retrieves images, condition on previous failures, users mark model failures, and then over time, CLIP begins the hill climb towards high error regions. This iterative process is also helpful for users because it helps them to refine and form new hypotheses for model failure modes. For example, after 2 rounds of testing, this user rejects the hypothesis that stop signs in general are hard and revises this to stop signs covered in snow. Zooming out, users repeat this inner testing loop many times, starting with different natural language seed topics. To propose topics to explore, we use GPT-3, conditioning on previously explored topics with high failure rates. Users then steer testing by selecting topics from that list, which are promising and relevant to the downstream task. To evaluate AdaVision, we asked users to test 3 state-of-the-art models across image classification, object detection, and captioning tasks. We compare AdaVision to a CLIP retrieval baseline that is non-adaptive, similar to unassisted red teaming with an image search engine. Users find nearly twice as many unique failures with AdaVision than without. We also verify that topics with high failure rates found in AdaVision testing generalize to held-out data. That is, if we take those topics and collect additional images from the topic, the model maintains high failure rates, suggesting those topics are genuinely difficult. The failure rates are often higher than topics proposed by other fully automatic methods. We also show that fine-tuning classification models on user-found bugs from AdaVision testing fixes behaviors on those topics, all while maintaining in-distribution ImageNet performance. As a nice side effect, we also find that this improves out-of-distribution performance across 5 OOD evaluation sets. To learn more, we invite you to check out our paper found at that QR code. We'd also love to see you at the poster session or the oral presentation slot on Wednesday at ICCV. Thank you.